So it's a pleasure for me to introduce to you Ángeles Vázquez from the Universitat Autónoma de Barcelona, where she's actually a colleague of Andreas, and they have some shared experience working together, translating, in a sense, similar to what, the work that Moritz did, information theoretic concepts into practical, like theoretical system design, but really where information theorists work with a generic transition probability matrix or some generic quantum channel, which has properties like being, I don't know, degradable or being entanglement breaking. And this is kind of the terminology that's important. In this line of work, one is more concerned with actual channels, like how does a photon get from A to B, what's the beam divergence, and so on and so forth. And it's very important to make this connection, I think. So it's a great pleasure for me to welcome you here. And with that, the stage is yours.
Thank you so much. It's really, really nice to be here with experts of this. And I hope not to not disappoint you, because since he told me just talk about your ideas, the presentation is not really technical. I don't want to give you my technical stuff and how nice are our channel models and all that, but it's more about provoking a little bit. And so it's a little bit high level and with the objective of discussion. So the idea that I want to put on the table is to integrate the concept of crypto agility with physical layer security. And presentation is basically to explain what I mean with that. And then also maybe it's important to say that I am an engineer, but a theoretical engineer. So that's why maybe the perspective is also a little bit different. So then, first of all, I want to give the motivation of why crypto agile design and where does it come from and what we propose. And then the idea I put on the table is to integrate post-quantum cryptography and physical layer security, but what I mean with physical layer security is physical layer security, because QKD is also physical layer security, and QKD works at the physical layer, with the quantum protocol, and then just an example of use case, space, because it's my field, space communications, and then basically all this is to highlight what are the challenges ahead. So the first part for this audience maybe is a little bit redundant, but motivation of crypto agile design. As we know, the motivation is quantum computers. And then we know that these asymmetric protocols are threatened already. And then now we go with what are the solutions. So first we have the solutions as proposed by the NIST, where they reason that there is no immediate threat to post-quantum cryptography, and therefore, so this is their main focus. And then there is this other solution for this threat, which is, let's say, if the previous one is some sort of American perspective, then this would be like a little bit European perspective, in which at the physical layer, we can go to quantum technologies, in particular quantum key distribution. But with this quantum key distribution at the physical layer, which is proven secure, but as a key provision for the symmetric key protocols. And then what we try to propose here is that actually what we can do is not only to do this EuroQCI with QKD, but with any protocol, any cryptographic protocol at the physical layer, either classical or quantum. So then why we propose this and why we think it should be done like this. So both Europe and US are recommending that the roadmap to the transition to post-quantum cryptography has to be in this way. They say the EU Commission encourages hybrid schemes that combine post-quantum cryptography with existing cryptographic approaches or with quantum key distribution. So what we believe is that what this means is that we may need to do cryptographic hybridation, which means the deployment of QKD, but not QKD, but physical layer security, to be combined with post-quantum cryptography. So then, in doing this, to combine everything, then what comes in is this concept of crypto-agility that this has also proposed by NIST, and that's why I borrow their slides. These are NIST slides, and because this is their view of what crypto-agility is. So first is the ability for machines to select their security algorithms in real time and based on their combined security functions, which means that the way we work now with QKD, with physical layer security, you see, okay, now is the guy on the physical layer security, now is the guy on the WhatsApp channel, now is the guy of QKD. So they believe, and I believe too, that since all of them has pros and cons, now what we should do is to hybridize them all and take it into account in the overall design of the protocol. So then is also the ability to add new cryptographic features or algorithms to existing hardware or software, meaning that the crypto-agility should be at the algorithm level, but also hardware level, because sometimes to implement the same algorithm that change a little bit, you also need to change a little bit the hardware. But this, in principle, it should be possible from an engineering point of view. The problem is that we are not used to thinking that way. And so then this would allow also the ability to gracefully retard cryptographic systems that have become vulnerable or obsolete. So then this crypto-agility also considers interoperability and backward compatibility, and prevents downgrade attacks, okay, because this can be done today. You know, in the recent days, we have seen that there are new attacks coming up that we are not aware, and it's like we are a little bit naive on how we are actually designing the cryptographic protocols. I think we need to think hardware all at the same time, and hardware and software at the same time too. Yeah, and crypto-agility has been considering them as a key for smooth transitions too. So what are the existing approaches and solutions? So we, whenever we build a protocol, we need to think how agile is the protocol, how if it is too much deterministic or too much involved, then will not be agile. So we should simplify and make it agile. Then we should look at the hardware agility, which means, okay, I have this protocol, this nice WhatsApp protocol or this nice QKD protocol, but what is the hardware I need? Can I switch from this protocol to this other protocol to this other protocol with the minimum the minimum change in hardware and the minimum change in algorithm, and where until which point we get the agility. And then the design agility, okay, because from the point of view when you are designing the protocol can also be enforced, this agility, and then API agility. And this basically these APIs are usually what the standardization of cryptographic protocols try to standardize. So then, and at the moment they are not agile. So there are several research areas that NIST chooses, like security analysis on protocols and countermeasures, security and complexity for systems, agility when the resources are limited, and limitation and potentials for repurposed cryptographic processors. So this is their view. Why? Because they are at the logical level, network level. Okay, so then what I try to convey here is how to translate this upper logical view of NIST to transfer this crypto agility idea to what we do. No? Quantum protocols, physical layer protocols. This is the idea. So then the idea is this: to integrate post-quantum cryptography and all the physical layer securities we are doing with a crypto agile point of view. And then it happens that there is already a protocol that is called the Muckle protocol, Muckle Plus protocol. Does anyone know this protocol? One, two people, three, good. You know, because I think it's really important, because exactly this protocol is doing what I'm trying to put on the table, but without physical layer security. So let's say that what I'm saying here is that we even enlarge this by making it even more agile by introducing physical layer WhatsApp channel protocols. That's the idea. And just to have, because the Muckle protocol is not easy, it's not easy, but just for you to get the gist of it. So what they do is they propose to use multiple sources of keys, classical, post-quantum, and QKD as part of the same protocol. So and then they classify like this: secure against the classical key, secure against classical attacks; post-quantum key, secure against quantum attacks; and the QKD key with information theoretic security, which means that each of them has different type of security definition, security mathematical underlying framework, and algorithm framework. So that's a big thing, how to put all these things together. And then they combine them and they define several functions and mechanisms, and they more or less they do the security definitions. But I believe this is still some work to do. But as far as I know, it's already in its way to standardization. So then the proposal we have made, and what I'm presenting here, I've been presenting also in this cost action that just started last year, which is called Physical Layer Security for Trustworthy and Resilient 6G Systems. So I propose a specific task group. Why? Because we need to work with crypto people, with quantum people together. And the first idea will be to combine PQC with physical layer protocols, meaning the Muckle, but plus the physical layer WhatsApp protocols. And then what we would like is only crypto agility at the physical layer. It's not what the NIST is considering, but our proposal is that it's also useful. It's very useful. To not, when you design your system, you have all the subsystems that make the protocol work, and then you realize that most of these subsystems are the same subsystems that will be needed for the physical layer protocol, for the WhatsApp protocols, are exactly the same. So the only thing is to consider that how to make the crypto agility. Then, for example, use case space is my field. So there are, for example, for in this here, combine QKD with quantum physical layer security. The idea here is to combine QKD with quantum WhatsApp protocols. quantum physical layer protocols, because I insist the subsystems, the hardware are nearly the same. And in this particular case, we are working with these two protocols that we have with this the newest the one from 2024 is with Andreas, that he is not here. He told me he was here, but he's not here. Yes, he told me that. Yes, yeah. So then you see, this is the system model for this for these protocols. So you have coherent states that you modulate, and then you have the quantum channel, the legitimate quantum channel, and the if quantum channel. So in principle, also very similar to the quantum phase of quantum key distribution. And then the level of security of these protocols depend on where are your assumptions, both for B and for E, because you may assume different detections for if, or that if is good enough to be only quantum mechanics limited, meaning that she can access all the quantum information, which is totally nonsense from an engineer point of view. But if physicists are happy with that, then we also consider that if can access all the coherent information that is in the. So then the idea, so once we have these protocols, our idea now is to combine them with QKD under this crypto agile framework. Now, but what are the challenges? Because for me, this is the main slide. Because okay, we got what is the crypto agility concept, but I am concerned always with the security certification, with the security warranties. Okay, because in engineering we have to guarantee to the customer that that a system is secure. So what I like to guarantee security is to measure and to give a number. So as you know, in QKD, this number, I am always asking why 10 to minus 12 and not 10 to minus 15 and not 10 to minus 20. It's quite arbitrary, in my opinion. Okay, but then if you go to this, so this is a quantum community. If you go to the physical layer community, then we have information, a lot of information theoretical metrics, such as this finite length information theoretical security metrics. But what happens is that there are different theoretical frameworks. For example, there are the second order method, both for classical and quantum Shannon information theory. Then we have the exponent method, both for classical and quantum information spectrum information theory, which is not the same as Shannon theory. And then the smooth mean entropy method, which has been invented for QKD. And this is quantum information theory. So at least there are these three theoretical frameworks. So for me, this is a logical contradiction, because how you can guarantee security if there are different people using these different frameworks, but they just give you a number. For me, this is the key issue to make security warranties for QKD, for physical layer security, or for this crypto agility. And then not only you have the theoretical frameworks, but within each theoretical framework, you have different security metrics. For example, the ones related to second order method, for example, strong security, they're related to exponent method, which is the exponential decay of strong security, which is my favorite one, because each of us has a favorite. For me, this is because I see everything logically well deducted. I can prove this, what is the meaning of that, okay? But then there is these other two methods, like, for example, smooth mean entropy, which is so difficult to compute that then there are so many ways to go around this difficulty, that then you have as many papers as options of how to get around this difficulty of computing this smooth entropy. And finally, since you have all this mess, then you have the methods which are called security proof, because when you are in the quantum discussions, then you get this socializing thing in which you ask, okay, and what is your security proof? Mine is this one. Okay, nice. I am using this other security proof. Okay, and for me, for example, I am now in this project, national project to build QKD over LEO satellite, and again, I am concerned about how to guarantee the security of the system, and then we need to navigate around all this. So then this is a challenge in the only in the quantum layer. And then, as you know, above the quantum layer, purely physical, you have what they call the quantum key management, in which you have the quantum layer, you get a few bits that are very nice quantum secure, but then suddenly you can go through all the internet and transfer as much as possible all these keys. So it's a little bit challenging how you can guarantee the final security here. Okay, so you have already standards. This is such a nice architecture is part of this series of standards, and they have logically perfect architectures. Yes, you see that the key will reach there for sure. But they say nothing on how the security can be guaranteed. So this is a challenge. Okay, in my opinion, this is a challenge, and that's why the crypto agility then faces this challenge and says, okay, it's true. This is difficult. This is difficult. How we can put together and guarantee security that is reasonable for all the communities. And this is why in this that I told you, this in this cost action, we have put together a few completely interdisciplinary people to be able not to understand each other and to put together the different frameworks. Now the conclusions, I just want to make clear that I translate the message that the crypto agility framework allows integrating classical and quantum, QKD and physical layer and post-quantum cryptography. But then the challenges are guarantee security at the quantum layer, real-world security proofs, guarantee security at key management layer, guarantee security at global dynamic level, and how to integrate security metrics. So that's all what I said actually.
Yeah, thanks for your talk. I am curious, are there already like implementations that perform such tasks? Like I'm specifically curious about the agility of kind of change component. Like it sounded like you're scoping for a very modular system where you can change stuff on the fly without interrupting the actual production system, basically. Do you already have setups like that
No,
that are working?
Not yet. Not yet. There are, we have in this construction, we are working on that, of course, and we have several options now, but we don't have yet the final. But yes, the modular design seems like the more logical one.
The architecture overview you showed, is that going to be an ETSI standard, or is that
that architecture?
Yeah,
is ITU standard.
Okay.
I don't know if it is ETSI 2. Do you know? Is ETSI 2? I guess.
You find it on the web.
But you know what? The authors of these ITU standards are European. The authors of these standards are European.
Okay.
You know?
Thank you.
I was going to ask, which attacker model are you using? What can the attacker do and what can't the attacker do?
what type of attacks we consider for this.
What abilities does your attacker that you're considering security against have, and what abilities do they lack?
Yeah, this is you are welcome to come with us and study that thing, because this is just, I came with the idea. We don't have we still don't have the solution. We don't have the solution. The idea is that we with the to be prepared. The cryptology means also to be prepared to the attacks that you don't know. Because in these ITU standards, you have pages and pages of attacks, but then tomorrow there might be a new attack. So in cryptology, you are prepared for attack that you don't know. You detect something wrong and you change and possibly abort.
So if I may respond there, I mean, when there is a cryptographic system, or when there is a physical layer security system, there must be some implicit attack model. There's a set of things that are going to break the system, and there's a set of things that are going to leave it unharmed. And I mean, implicitly, you can work backwards from that and construct the attacker you have. And that's something that, because this system looks like something where you could have QKD there, and then you can put another thing there, and another thing, and another thing. So there's kind of this question in this N+1 setup, where do you stop? And I think getting that N+1 question empirically really down, that's like what I'd be interested in about in an attacker model. Just know when to keep going, when to stop.
Yeah, but that's why, due to what you are asking, this is the reason why I divided things into physical layer and above. Because since I work in the satellite, we've seen that the attacks that affect us are not in the standards.
So with that ITU architecture and the key management layer, right? So from what I understand in talking to the optical system vendors, the fiber guys, right? That's what they're implementing. And I have this sense, what you're saying, that maybe there's holes in the standard that it doesn't cover things end to end, but is that something where the system vendor should be guaranteeing it end to end, that
No.
it's up to them, or you think it should be standardized? Yeah.
No, it's not. I don't think it's up to the vendors, because I work with vendors, and poor guy, they really need these inputs. Okay, well, how does this work? So one thing is that if you trust the supply chain, right? That's one thing. And another thing that I'm talking about is more logical. I mean, the mathematics of the security, and how you carry over the mathematics from the quantum layer up to the logical layer, and through all these.
Historically, at the classical case, I mean, they have key management systems and they do all that. And I thought that the optical system vendors were responsible for ensuring that their key management system was secure and reliable and this sort of thing, or is it?
I think if you introduce quantum, it's different to that.
Okay.
It's different.
Okay, interesting.